Okay. So welcome everybody. It's a big pleasure to introduce you Professor James Binney. James Binney graduated at Cambridge University and then he moved to Oxford for making the PhD. And then he went to the States at Princeton University where he was for a few years. And then he, in 1996, became professor of physics at the Oxford University. He has been awarded with several prizes. I want to just simply mention the Maxwell Prize and medal by the Institute of Physics in London, and also received in 2003 the Brouwer Award of the American Astronomical Society. So he's also well known by some books that he has written. I would just mention those that you know already. One is Galactic Dynamics in collaboration with Scott Tremaine, and the most recent one, which is Galactic Astronomy, also done in collaboration with Mike Murphy. So he's an expert on structure, dynamics, and formation of galaxies, and he will stay the full day with us. So if you have any question or you want to approach him and talk with him, just either go to him, which is in Ramon's office, or come to me and I will organize a meeting for you. So thank you very much, Professor, for coming.
Okay, so I want to talk on this theme today, and I should first of all explain why. So here is my outline. See if this thing, yes, it does. Here we go. I'm going to talk about surveys, which is the sort of observational to the work that I'm talking about. Then I'll talk about the goals, what we want to achieve with these surveys, how we have to do this logically, what the requirements are on the models that are imposed by these considerations. And then I'm going to try and I'll give you a very brief outline to the particular approach to doing this, to modeling that we are pursuing, we are developing in Oxford and have been for a number of years. And then I'll talk about some early results from the SDS that have emerged from looking at the SDSS and most recently the RAVE survey data. So why is it very important to improve our modeling technique at this time? Well, we live in this era of vast surveys. We're in the middle of an era of vast surveys, which I think you might say started, from our perspective, it started with something like the two-mass survey and the Dennis survey in the photometry in the near-infrared, and is continuing through the UKID survey and the Vista hemispherical survey, which is just barely getting underway. And I'm sure that this progression will continue at least to the end of this decade. Then there have been huge spectroscopic surveys, most obviously the Sloan Digital Sky Survey, driven by cosmology, but many of the most interesting results have come out of almost its waste product of studying stars within the galaxy. Then we are about half of the way through the RAVE, the Radial Velocity Experiment survey, which is an international project to gather up of order 1 million stellar spectra within a couple of few kiloparsecs of the Sun. The SDSS led to the Segway survey, which is now just about complete. In Australia, the Hermes survey is now being planned. So this is a near-infrared, medium resolution spectroscopic survey to look at chemical abundances, and the Americans are planning something slightly similar, the Apogee survey, also near-infrared spectrometry, and again spectroscopy, and I'm sure that this will also continue. So there have been huge surveys to look at to gather the spectra of stars. On the astrometric front, the revolution started with the Hipparcos satellite, which I guess reported, we had the first important results from that about 15 years ago now, that sort of thing. The Hipparcos survey enabled the US Naval Observatory to recalibrate ancient plates and produce a series of catalogues with huge numbers of proper motions, the most recent incarnation of which is the UCAC-3, which was produced last year. We are just at the beginning. Pan-STARRS in Hawaii is just barely getting underway. It's just about now functional and is going to is potentially very exciting from the astrometric perspective. And we are, of course, looking forward to the launch of Gaia at the end of, early 2012 probably. which will do astrometry for 1 billion stars or so, and after Gaia, there will be some kind of infrared analog, some kind of analog astrometric survey done in the near infrared so that you can penetrate towards the galactic center and more broadly within the galactic disk than Gaia will be able to do, because Gaia works in the visible, and the Japanese have a program under the heading of Jasmine to explore that, to develop such possibilities. So what we already have is about 10 to the 8th. We have photometry of something like 10 to the 8 stars. We have proper motions of something on the order of 10 to the 7 stars. We have spectra of something on the order of 10 to the 6 stars, and trigonometric parallaxes on the order of 10 to the 5th stars. But by the end of the decade, we're going to have trigonometric parallaxes, the weakest part of this, for on the order of 10 to the 9 stars, and probably spectra for something like 10 to the 8 stars. So there's an enormous body of data. We already have an enormous body of data, and that body of data is growing rapidly, and by the end of the decade will be truly stupendous. It's huge resources have gone into this, and it's essential that we get the promised science out. What is the science? What do we want to know? Well, it's a long list, of course, and people in this room will have other perspectives which will require other things, but here's a list of fairly obvious items. We want to know most crudely, so what are the scale lengths of the galaxy's thin and thick disks, both in the plane and vertically? We want to know what the velocity field is within these disks. Within the thin disk, how you might say almost the circular rotation varies as a function of radius. In other words, we want to know the rotation curve of the galaxy much better than we do. Our galaxy has a rotation curve that's less well determined than that of most nearby external galaxies. We want to know how streaming motion varies as you go up away from the galactic plane. This is very controversial and interesting. We want to understand the spiral structure of our galaxy. Maps of the spiral structure of our galaxy, are now in that state which maps of the globe were in before Christopher Columbus went to America. It's that bad. There's sort of there's a sense that we know roughly what happens around here. You know, the Iberian Peninsula is there, that's clear, but you go a small way beyond and somebody says this thing, somebody else says that thing. Roughly speaking, there be dragons, it's not clear. So we need to know what the spiral structure of our galaxy is, and not just know where it is. We want to know how fast it's moving, what dynamics does it impose on the gas and the stars, and so on. We want to know the distribution of chemical elements within stars. I think we're at a point where our picture of the chemical evolution of the galaxy is changing quite rapidly, but chemical evolution, the distribution of chemistry, the distribution of elements amongst stars, is a fundamental key to deciphering how the galaxy was put together. And of course, we want to know how the galaxy was put together because it's a very typical galaxy. It's not just any old galaxy. We want to know the morphology of the bar. We know that at the center of the galaxy we have a bulge bar. We live in a barred galaxy. It has a bulge bar, but especially from this institution, there have come persistent reports that there is a so-called long bar within the disk made of disk objects. The relationship of this to the short classical bulge bar is very unclear. The relationship of either bar to spiral structure is very unclear. These things we need to be pinned down. At the moment, we have too much rumors and not enough completely established fact. We want to know the gross and fine structure of the stellar halo. So the SDSS has taught us that the classical stellar halo of the galaxy is a very unsmooth and irregular thing, full of streamers, full of features of one sort and another. We want to really understand what those features are and what we can learn about the assembly history of the galaxy from those. Almost crucially, and it's in the middle of this list, but really in a way should be high up, we want to know, well, what is the gravitational potential of our galaxy? What is the gravitational field of our galaxy? Because currently and foreseeably likely, the only way we have of mapping the crucial dark matter distribution within the galaxy is by studying, we need to study the matter distribution of the stars in exquisite detail so that we can find which part and we need to study the force field within the galaxy in exquisite detail by doing dynamics, in order that we can find which part of that force field is generated by the dark matter distribution, and by taking the divergence of that force, find out what the density of dark matter is around the galaxy. It's obviously a fundamental thing to know where most of the mass of the galaxy is, and we really don't have very good prospects of finding this anyway, except by this very careful work on the force field of the galaxy and the mass distribution of the baryons within the galaxy. We want to know what the distribution functions are, so that's in some sense, the number of stars per unit phase space of some number of stellar populations. And this number n at the moment would be maybe the thin disk, the thick disk, the halo. That's the kind of crudest characterization of the galaxy. But as we go forward, we will undoubtedly want to make finer distinctions. We will want to talk about the alpha-enhanced thick disk and the metal-rich end of the thick disk and the metal-poor end of the thick disk. And so we want to break it up into a more precise list of components, and each of these components will have a distribution function. So this, you'll see later on, this label alpha labels which population you're talking about. And as I say, at the moment you would have a very crude representation in terms of a few populations, but as you went forward in time and you understood more about the galaxy, the number of populations would be, that you wish to represent the galaxy as made up of, would be increasing. Of course, we want to know the history of the galaxy. We want to know how it arrived in its present form. We want to know how important merger events were in this history, how important secular heating was. We know that the random velocities of stars increase fairly smoothly over time. How smoothly over time is still somewhat controversial. I would say pretty smoothly over time. We want to know how much radial migration there is. Was the sun born at 8 kiloparsecs? Was it born at 6 kiloparsecs or 4 kiloparsecs and moved here? It seems quite likely that it was born at a smaller radius and moved here. We'd like to know more about that kind of thing. We'd like to know, we'd like to characterize the diffusion coefficients in phase space. We'd like to characterize the diffusion in phase space that causes stars to move from one circular orbit to another and move from circular orbits to eccentric and inclined orbits, because this encodes the history of the spiral structure of the galaxy. So these are all things that we want to get out of these surveys. Now, how are we going to do this? Well, I believe very firmly that we have to launch on what's essentially a new technology in this area, which is to carry the models into the space of the observables. And this is a very, very trivial example to explain why I think this is a crucial thing to do. So the issue is that distance errors in astronomy are always serious. I mean, they're always there. They never go away. And they're typically always serious. The reason they're always... So, for example, Gaia is designed to do trigonometric parallaxes, the ultimate distance determining tool, right? That's the gold standard of the business. But, of course, the accuracy with which Gaia determines the parallax of a star depends on the apparent magnitude of the star. It gets 17th or 16th apparent magnitude stars it pins their parallaxes down pretty exactly, but by the time you're at 20th magnitude, it's becoming more uncertain. And because the number of stars always increases as you go to fainter apparent magnitudes, this means that it doesn't matter what astrometric survey you launch on, most of your stars have bad parallax errors, have substantial distance uncertainties. So, and of course, there are spectrophotometric, whatever, techniques for determining stars. And again, the same issue holds, that there are always loads of faint stars, which the data are rather poor, and you have large distance errors. Now, if you've measured, say, a negative parallax for a star, which is obviously impossible. I mean, you can't say the distance is 1 over the negative parallax. That's ridiculous. That's hopeless. But a negative parallax is still a valuable piece of information. It tells you the parallax of that star is small, smaller than the observing errors. So it's information, and you have to use it. If you insist upon taking all your parallaxes and turning them upside down and declaring them to be distances, you have to throw that star out. And this introduces all kinds of unpleasant biases in your sample. It's not a good thing to do. You must work in the space of parallaxes. That's what you've measured. And the proper procedure is to carry your model into the space of the parallaxes and then to do the fitting there. And here's a little toy example of how important these what a mess you will make if you try and carry the data into the physical space that you wish to think about, into the space in which you do physics. So we want the space in which we do physics, in the case of the galaxies, the phase space of stars. It's the position and velocities of the stars. Okay, so supposing we were imagining a shear flow, supposing that velocity as a function of distance s were equal to some constant velocity plus some object A, which has the dimensions of a frequency, times distance. Okay, so this is, of course, for example, if we're looking at the motions, the classical problem of motions within a differentially rotating disk, this is exactly the kind of thing that we're doing. So I've just simulated this in a simple way. This is proper motion here, this is distance here, along horizontally, sorry. And the actual relationship I happen to have chosen, I've chosen a particular value for V0, a particular value for A, so I find proper motions, which is a function of distance, should lie on this curve here, which I'm having difficulty drawing. So the proper motions become very large as the distance becomes small, because V is the proper motion mu, being V over S, is obviously V0 over S plus A, and they asymptote to this constant A at large distance. So then, of course, what have I done? I've sampled this distribution, that's what the dots are, to provide pseudo data, and then I've scattered them by 20% errors in distance, which is not a large distance error in the real world, right? One often has distances that are less good than that. Mostly one has distances less good than that. And then over here, I've said, okay, so now we observe. I haven't put any error in the proper motion at all. I've just made an error in the distance, a 20% error in the distance, so scattered 20% either side of this line. I have then, in this diagram, said, supposing we measure these proper motions and we interpret them as, we measure these proper motions at these measured distances. Let us now look at what the predicted velocity is from the proper motion of these same stars as a function of distance. And you see that the velocity now has something like a 40% error, because you made an error twice. You make an error in assigning a distance, and then you make an error given the wrong distance in assigning a velocity. And you quickly get into a real muddle. And I've already spoken about the problem of interpreting negative parallaxes. So we don't want to do that. So what we want is in order to interpret these data, we do not want to do what, for example, Izvezic et al. Do with the SDSS data. They do it very beautifully, but it's not the correct, I would argue it's not the way forward in the subject of taking your star counts, taking your data and inverting them into a three-dimensional distribution. You want to have a well-defined model, you want to put it into the space of observables, and you want to fit the model in the space of observables to your data. So what do we need? We need a hierarchy of dynamical models which vary in complexity. Now, I think this issue of the hierarchy is very important. The galaxy is enormously complicated. We sit inside it and observe it in principle, or can observe it in exquisite detail, at least its local manifestations in incredible detail. And we measure a huge number of variables. Here is a short list of just 10 variables, right? So most obviously there's a distance to a star, there's a longitude, there's its position on the sky, L and B, there's its line of sight velocity, these shouldn't have been written as V alpha, V delta. These should have been proper motion in the right ascension, proper motion in the declination direction, right? Then other obvious things, the star has an apparent magnitude. Of course, it has several apparent magnitudes, but let's imagine it has one apparent magnitude and one color. It has some kind of Fe over H, some kind of metallicity. In fact, it has many chemical abundances, Fe over H, it has alpha over Fe, it has a barium over something else. But let's keep life simple. So this is a minimal equipment. It has a log G, it has some kind of surface gravity from the spectrum. Already here, with this absolutely minimal thing, I have 10 measured quantities, 10 variables. And as I've said, the real list is much longer than that if you've got quality data. So the problem of fitting of interpreting these data is very complex, and we must proceed. In order to make progress, I believe, we need to have simple models that we fit to the data. And we get the broad outlines of the data represented, and then we ask ourselves in which things in the data which look like signal am I not yet fitting? And then I want to refine my model, introduce some additional thing, like I might introduce some spiral structure to try and to account for the most serious mismatches between the data and the model, and so on, and keep going, refining until I feel either I'm bored, that basically the rest is not interesting, or, of course, in principle, I've achieved complete victory, but in practice, we will always give up at some point and say, well, you know, we've got 99% of this, and the rest is weather. It's not interesting. So what we need is a hierarchy of dynamical models, and we need an apparatus to fit the models to the data in the space of the data. How are we going to get these models? The traditional and obvious approach, or a traditional and obvious approach, is an n-body model. These models, I should say, need to be, I haven't really made this point, but they need to be dynamical. There are two reasons why they need to be dynamical. Let's say, I mustn't just say there are so-and-so many stars in phase space. I must say there are so-and-so many stars in phase space, and they are distributed in a way which is consistent with Newton's laws of motion. The reason I have to insist on this is because I want to reduce the dimensionality of the problem. If I say that I can distribute the stars any which way in phase space, it's a six-dimensional space, and there's an enormous amount of freedom. There's too much freedom. And another crucial aspect of this is that if I want to obtain the gravitational potential of the galaxy, as I do because I want to track the dark matter distribution, I need to assume that the galaxy is in something like a steady state. If I assume it's in something like a steady state consistent with some potential, then Jeans's theorem reduces the dimensionality of the problem to 3 from 6, which is an enormous economy. It takes away a huge amount of freedom from the models, freedom which isn't helpful. So I want to make a dynamical model, and if I want to make a dynamical model, n-body models are an obvious way to go. What are the advantages of n-body models? They're flexible. I mean, you can make all kinds of different galaxies, and above all, they're very easy to relate to cosmology. We are not yet quite in the position where, starting from realistic initial fluctuations before recombination, that we can reconstruct, that we can project forward in time to a realistic galaxy. But we're nearly there, and in, say, 10 years, I think it's reasonable to think we might be there. But there are drawbacks. One is it doesn't deliver the distribution function. What you get is an n-particle realization of a distribution function. So you have one sampling of something which is fundamentally statistical, and matching one sampling of something that's statistical to the one sampling of the galaxy that we actually have is a hard thing to do. It's much easier to match the one galaxy that we have to a probability distribution, to the probability distribution which underlies an n-body model, but which you don't know what it is. So the distribution function is the incarnation of that probability distribution. So I want that distribution function in order that I can match, I can ask easily or relatively easily, whether the galaxy, the one and only galaxy that I can see, is consistent with that distribution function. It has limited resolution, even if you have, if you have millions of particles. In the tiny little solar neighborhood, you don't have that many particles. An n-body model is very difficult to control. If you start with cosmological initial conditions, the galaxies that you end up with, or the galaxies that you end up with, are sort of chosen for you by your initial fluctuations, but in some incredibly complicated way. And if you produce a galaxy that looks a bit like the galaxy, a bit like the Milky Way, but isn't quite right, the details aren't quite adjusted as you want, it's not clear how you should change your initial conditions in order to generate a respectable model which fits better the data. It's not an easy object to control and maneuver the model so it looks more and more like the galaxy in higher and higher detail. And another issue, which I think is a very important one from the perspective of the scientific process, is that it's difficult to characterize an n-body model. An n-body model is defined by the 6n, so 60 million or 600 million phase-space coordinates of the particles. But it's extremely non-unique, because if you integrate the n-body model forward in time, the phase-space coordinates of the particles change, but the n-body model does not. So if I have an n-body model and Volker Springel has an n-body model, it's difficult for us to say in which way our n-body models differ from each other. And so it's not helpful for the scientific dialogue. So an n-body model, yeah, okay, so I think that's enough said. They're difficult to characterize. Okay, so an alternative technique that's very widely used in modeling external galaxies that are observed in detail, for example, in the Sauron project, looking at early type galaxies, is the Schwarzschild model. So where we basically integrate the orbits, we integrate equations of motion in some given potential to find orbits of stars, and then we look for a weighting of those orbits so that if we add in stars on those orbits in the numbers that we've chosen with those weights, we get a good representation of the observables. Well, what we want, as I've said, to have the distribution function. I'm fixated on having the distribution function. By Jeans's theorem, as I've said, the distribution function is a function of the integrals of motion. What integrals of motion should we use? Already Jeans, in 1915 or whatever, knew that for the Milky Way, the classical integrals, the energy and the angular momentum around the symmetry axis, are definitely not adequate tools. I mean, the distribution function isn't a function only of these two. Now, in the Schwarzschild method, basically the idea is that you characterize the orbits by their initial conditions. So the distribution function becomes a function of initial conditions, if you're lucky, if you do it well. But the initial conditions are seriously non-unique. That's the same problem, basically, you have with the n-body model, that we have a Schwarzschild model with an orbit library chosen with these initial conditions. Somebody else has an n-body model, has a Schwarzschild model. They have a different procedure for determining the initial conditions, so their weights look completely different from our weights, but we may have exactly the same model, but we don't know. And if our models differ, we don't know in what respect they differ. And it's because the initial conditions are not unique characterizations of orbits. So this makes the comparison of models difficult, and as I say, we do want to have that distribution function. So our approach to this problem is what's called torus modeling, and I should now try and explain to you what this is. So instead of finding orbits as a time sequence, x of t, v of t, by integrating the equations of motion with a Runge-Kutta integrator, which is the sort of classical approach of Schwarzschild, we obtain orbits, and I'm not going to go into the technology of this because it's a talk or a couple of talks in itself, but we have a numerical procedure which you can think of. It's just code. It's just computer code, which you can think of as a replacement for, say, a Runge-Kutta integrator or a leapfrog integrator. It's the logical equivalent of that. But what it returns is not a time series, x of t, v of t. It returns you x for each orbit. The orbits are labeled by these things j, I'll talk about in a minute, as a function of theta, which are three phases. So the orbit becomes not a one-dimensional object that you move down in time. It becomes a three-dimensional object, a bit like the interior of this room, characterized by three phases. Okay, I think that's all I want to say about that. The subscripts which are labeling orbits are, so they're labeled by three isolating integrals, J1, J2, J3, which have special properties. They're unusual isolating integrals called actions, and these things here are the angle variables. There are three of these. These are the three phases that are analogs of, so the orbit's like the interior of this room, and where you are on the orbit is characterized by your x, y, and z coordinates, if you like. Those are your theta 1, theta 2, and theta 3 coordinates. And the thing about these coordinates is that they increase linearly in time. So if you represent the orbit by the inside of this room, the star, as it moves in time, moves on a straight line from one part of the room to the other part of the room, and the room, the funny part is that when it gets to this wall up there, because the room has periodic boundary conditions, that piece of the room maps it up to there, and it continues in a straight, it disappears over there, reappears over there, and continues in a straight line. And the ceiling is identified with the floor, this wall with this wall, the back wall with the front wall. So we have this very simple motion within this. So once you have possession of these things, you can find out where your star is at any time very simply, trivially, in fact. These action integrals are essentially unique, which facilitates comparison between models. These actions are adiabatic invariants. That means if you slowly change the gravitational potential, as the gravitational potential of the galaxy will be slowly changing because cosmic infall is increasing the mass of the disk all the time, for example, the actions stay fixed. So you can map orbits to orbits in different gravitational potentials. So you can study secular evolution very easily. And as I say, we have code which takes the actions as input and returns as output analytic functions for x of theta and v of theta. And you should think of this as a replacement for the Runge-Kutta integrator. Now there comes the question of, so our modeling approach is similar to the Schwarzschild modeling approach, except we don't use time series for orbits. We use these three-dimensional representations with the action and angle variables. So what we have to do next to make a model is we have to assign weights to these orbits. In other words, we have to choose a value of the distribution function for each value of j that we, for each value of the actions that we choose to use for a grid. So, oops, sorry, I've made the mistake of pushing the wrong thing backwards. So we could just proceed as Martin Schwarzschild taught us. Oh, I've done it again. Sorry. Hand-eye coordination. Here we go. Well, we could proceed as Schwarzschild said. We could seek non-negative weights W, which would be, so each orbit would have a weight W. Orbits are labeled by J, so there'd be W of J, such that our observational constraints were satisfied by the weight of the orbit times the contribution as O, J, and K of the jth orbit to the kth observational constraint. You know, so K might be the density in some particular cell. It might be the mean velocity in some cell. Whatever. Right? That's the traditional approach. We could do that, and then basically our model would be characterized by these weights W of J, and we might have, who knows, 100,000 orbits, say. So we would have 100,000 weights, and our model would be characterized by 100,000 weights. And the discussion between groups would be possible because we would have a unique characterization of our orbits, which could be understood in another institute. But in fact, I think it's better to proceed with fewer parameters. We don't really want to have this many parameters. We want to have a smaller number of parameters that speak to us as astronomers, at least in the early stages of the modeling. Maybe when we are refining our model around 2030 into some master model, we might want to use this approach. But I think for a long time we won't want to do that. What we will want to use is simple analytic distribution functions for each component of the galaxy. And I want to, because I'm going to show you now the very simple analytic distribution functions. So this is a function. What is this? This is a function, f of the actions, one for each population within the galaxy, which gives me the weight W of J. So here's a simple example from a paper that appeared very recently in Monthly Notices. Consider the vertical structure of our disk. So we've known. So here is the logarithm of the density of stars as you go up above the galactic plane over as a function of height in kiloparsecs. So 1, 2, etc. kiloparsecs. There are some conflicting data. The dots are Kuiken and Gilmore, 1988. Yes, back at the here is Gilmore and Reed, 1983. These points on the line, who showed us that there was a thick disk. So the classical evidence for the thick disk, of course, is that this profile isn't a straight line and exponential. It's curvy and can be well represented as a sum of two straight lines, two exponentials. Okay. So the exercise, and down here, what do we have? The histogram are the W velocities, the velocities perpendicular to the galactic plane in the Geneva-Copenhagen survey. That's a collection of F and G stars which have good Hipparcos parallaxes. So here's the histogram. So this is kind of the data. If you, given these, I've chosen to fit the Kuiken and the Gilmore and Reed classical points, density points. I've looked for a distribution function which reproduces those. And the distribution function that I'm suggesting is this incredibly simple item here. We're saying that here is the JZ is the measure of is the action associated with motion perpendicular to the galactic plane. So stars that stay in the galactic plane practically have 0 JZ, and ones that oscillate to 2 kiloparsecs have larger ones. So here is a distribution function which has only 2 free parameters. This V gamma is one free parameter. It's a constant with the dimensions of velocity. This is the frequency of oscillation vertically, which is something that the torus machinery returns. So that's not a free parameter. That's a function of J. This is a parameter, and this gamma is a parameter. And this thing on the bottom is just the integral of the top to ensure that if you integrate this with respect to Jz, you get 1, so that we can interpret this as a probability density. Okay, so I fitted these 2 free parameters to these data here, and that gives me the line that passes through the Gilmore and Reed things. Then you can, having made that fit, so I've fitted 2 numbers to those data points, the rest is prediction. Okay, so what then does the apparatus predict is the velocity, the distribution of W velocities for the Geneva-Copenhagen sample. Well, it's this smooth curve here, which I think is a pretty decent representation of the observational histogram. What does it predict for the velocity dispersion as a function of height above the galactic plane? It predicts this curve here, and this should be compared with a number of observational points, which at the time I did this work were as shown here. So we have from Bond et al., this is a study of the SDSS, we have this prediction. From Fuchs et al., which is another SDSS prediction, for essentially the same population, you have this result. These 2 results, I stress, are observational results obtained by this process I criticized at the outset of going from the data to the physically interesting space without any intervening model. They've done it in 2 different ways, and I don't frankly understand. I don't grasp how it comes that they obtain such different answers. Anyway, my model doesn't agree with either of them, but it does more or less agree with some ancient Kuijken and Gilmore points. But I haven't fitted it to these Kuijken and Gilmore points. I fitted it to this over here, and the rest is prediction. Now, a new result is this, that the RAVE internal data release, so this isn't published and can't be published because it's kind of private at this point, yields these points here. So this is about 200,000 stars from the RAVE survey with very accurate line-of-sight velocities. And distances, and crucially distances, spectrophotometric distances assigned to them by my student Ben Burnett, who's working on this problem. So that's what he gets for velocity dispersion as a function of height for the RAVE stars. And this is and here's the green line of my model. The red line is an analytic fit to the RAVE data. So insofar as this here was a prediction of the outturn, I'm reasonably satisfied with it. This is incidentally what the velocity ellipsoid looks as a function of position above the galactic plane, but there isn't time to talk about that. Okay. So there you see a very simple distribution function with 2 parameters fitted to one part of the data does a pretty good job at representing the other parts of the data. And it's a model which to some extent speaks to you. Okay, but we have by no means finished, because this is just describing the motion perpendicular to the disk. What about the motion in the disk? Well, this is unfortunately a complicated story, because we know that the thin disk is a superposition of populations of differing age. We know that stars start out with very small random velocities in the plane on nearly circular orbits, and then over time, through interaction with spiral arms and molecular clouds, their random velocities increase, their heat increases. So what we need is a distribution function, and minimally what we need is a distribution for the stars that all have a certain age. Because the ages of individual stars, that's not the point. I mean, we would like to, but we don't. That's not the point. The point is that theoretically, we expect there to be different velocity distributions for stars of different ages. These differences tell us about the rate of heating by spiral structure and stuff, so they're very interesting. So look, my approach to this is as follows. Supposing I've done it again. Right, this side. Okay, so look, here is a really simple distribution. No, this is... sorry, I want to go... Yep. Sorry, yes. Okay, sorry. This is, so now I'm playing a different game. I'm actually looking at both the motion in the plane and the motion perpendicular to the plane. The crucial thing is that I am trying to think of the disk as a superposition of populations of different ages. So what am I going to take to be the distribution function for stars of a given age? I'm going to take it to be just an exponential, e to the minus the frequency that the torus machinery returns times the action integral. So there's one free parameter here, and that's this velocity dispersion here. Well, it's a parameter with the dimensions of velocity dispersion. Okay, and this on the bottom is just the normalization condition, so this thing integrated up. For example, if I look at the F and G stars, the A and F stars, studied by Holmberg and Flynn, then you have these points here, and this curve, the full curve, is one of these models. You choose a particular value of sigma, and you get this model for the density vertically as a function of height. I also need to, so I want to augment this now with a result for the distribution for motions in the plane. Now, the motion in the plane, a star has an angular momentum, of course, and also it has a JR, a radial action, which tells how eccentric its orbit, how much it rattles in and out. JR equals naught, it's in a circular orbit. JR is large, it's on a highly eccentric orbit. And this is the distribution function that I'm trying to fix. It has a free parameter here, which is the hotness of the stellar population. It has a free parameter here, which is of no interest at all. It tells you about the mean rotation rate far away towards the center of the galaxy. So this thing here, this 1 plus tangent thing, merely eliminates stars which have negative LZ, effectively, right? Because if LZ is negative, given that L0 I've put to quite a small number, then we're looking at the than of minus a large number, which is -1, and so this thing vanishes. So this is just a factor that means that our stars are all moving around positively, and that's basically it. That's pretty it. That's pretty much it. So for a population of a given age, I have a certain velocity dispersion. Oh, and I have, I suppose, a certain surface density sigma. Okay, so we make the complete distribution function by adding, for the whole disk, by adding these isothermals, right? So this thing here stands for the isothermal distribution function characterized by a certain radial velocity dispersion I've just described. This is the vertical isothermal population that I've just described. You add these all together with an exponential weighting, e to the tau over t0, because you think there were more stars formed in the past. This rate of star formation, this factor represents the rate of star formation being an exponentially declining function of time with a time constant t0. This is a boring normalization constant. Don't worry about it. And then you take these velocity dispersions to increase like some power of time and to vary radially, sort of exponentially, so that the disk becomes cool as you go outwards. These are the sort of leading characteristics of the kinematics of the disk that have been known for a long time. You then fit the the thin disk is represented by a single isothermal population, because you think all the stars are very old. You fit these parameters in the distribution function. So the thick disk parameters have been fitted to these numbers of stars as a function of v phi, the azimuthal velocity from Bond et al., so the SDSS data. I don't think it's not profitable to spend a lot of time on that. The thin disk parameters are fitted to the Geneva-Copenhagen data, so this is rather more interesting. So this is the histogram for the phi velocities, the velocities in the direction of galactic rotation. This is the radial velocities. And the curves tell you this is my best fitting model. And you will object that these best-fitting models are not very good, and you will say that my distribution function is pathetic, and I should try harder, right? Because it's clearly not good. There are some things that are good. So why do I think this is the business? Well, for one, the vertical structure is looking good, right? This is the Gilmore and Reed data again. But the trouble here is I could easily make this a little bit broader and bring that peak down. But then I would make this broader, and this would go over here too much. So what's happening here is that the model is predicting more stars that are moving relatively fast compared to circular. The circular speed is here at 220, than are actually observed. And I struggled for a long time with this, thinking, well, so I got a bad distribution function, I should try another distribution function. So I tried another distribution function and another distribution function, and it was always the same stupid problem. This theoretical distribution would never agree with these Geneva-Copenhagen velocities. And then I thought, well, maybe the Geneva-Copenhagen velocities are wrong, because I'm not. And this is in fact the case. Now, the reason they're wrong is not because they're stupid in Copenhagen and Geneva. It's because they're stupid in Oxford, as a matter of fact. The trouble was, they believed, Danon and Binney, who said that the speed of the sun with respect to circular is 5.2 plus or minus some small error bar, right? And all the world has believed this for 12 years or something, right? We have a very large number of citations for this paper, and it's wrong. The reason it's wrong is very interesting and is explained in a paper by Schoenrich, myself, and Walter Danon that is on the archive, and I think is almost out in monthly notices. And there isn't time to go into this, but it is a reflection of the chemical inhomogeneity. The reason this happens is because there's a metallicity gradient within the disk, and that fools you. When you look at the matter when you do a classical analysis using the Hipparcos data for stars with small random velocities, which is what we did back in 1998. So what I think I want to just say now, because time is short, this is the detailed explanation, and I'd be happy to talk about that offline, but I shouldn't do it. The bottom line is that these models with the distribution functions have uncovered, I'm pretty sure that this is correct, they've uncovered this error, and actually the sun is moving almost 12 kilometers a second faster than the circular velocity. It's a change by about a 10 sigma change in our velocity, because the usual problem in astronomy, the errors are not Gaussian, and systematic error is the big enemy. Well, I want just very quickly to go over the question, of how should you do this fitting to the data. Just a word about this, how to make the point of how do we use the distribution function and how do we use these actions in a systematic way to fit the model to the data in the data's own space. So the obvious thing to do is to do a Bayesian analysis. So basically, we calculate the probability of what you measure given a particular model, and then we do some kind of maximization of that. So what is that? Well, that's going to be the probability. The thing is, there are measuring errors, and these measuring errors, as I've stressed, are always going to be significant. They're sometimes going to be devastating. In fact, you won't even have measured some things, in which case this formalism takes care of it by simply putting the error. This is the experimental error in some quantity, in some observable UI. You can put that to infinity, and so we just have a Gaussian distribution here. So this is the probability that the experimental error shifts a value that the star really had, u primed I, to the value you measured, ui. And then this in here is the probability that, given the model, that there should be a star with the observables u primed I. Okay, so that's an obvious statement. And then, because of the way dynamics works, you can turn this integral over the observed quantities right down into this integral over the theoretical quantities, over all possible actions, all possible phases of orbits. The distribution function, which I've stressed, depends on the actions, and I've got simple functional forms for, times this same boring Gaussian factor, where now this u primed I becomes a function, is a known function, I should stress, of j and theta. So the computer knows all about that. That's non-negotiable. Okay, so there is a big problem, though, because some orbits are invisible. Orbits, for example, because we typically imagine the SDSS survey, for example, that is looking upwards out of the galaxy in some kind of a cone. And stars that are strongly confined to the plane don't go very much above or below the plane and have apocenters which are inside the sun, or indeed orbits which are confined to the plane and have pericenters which are outside the sun, are never going to appear in the catalogue. They don't feature. So there are values of J for which we cannot hope, it's ridiculous, it's completely out of the question, that we could hope to measure the distribution function. And there are some orbits which just barely make it which just barely contribute to the data, and there are others which contribute very heavily to the data. So what we need is to define and can easily calculate, for a given survey, we can calculate a selection function phi of j, which is the fraction of the angle space of that orbit, which is visible in the survey. So we can easily determine for a given survey what this is, and then it's clear that we can only constrain the distribution functions, the function f, for values of j such that phi of j is bigger than some threshold. Now, what that threshold epsilon is a matter of judgment, whether it's 0.1 or 0.05 or something. But if too little of the orbit lies within the surveyed space, then we shouldn't try to determine f at those points. And then what we do is what we actually maximize. We change the parameters in f such that this integral is maximized when summed over all actions, so this is summed over all actions because of that. And this is a very practical procedure. This is about the sampling and stuff. I don't think I want to talk about that. I just want to make the point that there is a very well-defined procedure for doing this, and we are currently in the process of actually implementing this and applying it to the SDSS. Okay, so here are my conclusions, because time is very much up. We have a huge and rapidly growing volume of survey data for the Milky Way. The key observables, in particular the parallax and the proper motion, are very far removed from the quantities of physical interest. And errors in distance, or parallax if you like, corrupt estimates of all physical quantities. As soon as you've made an error in distance, your error in practically everything, your absolute magnitude, your velocities, they're all badly wrong. So inversion of the data to make a physical model, I don't think is the way to go. What we need to do is we need to fit models to the data in a space of observables which is typically at least 10-dimensional and easily bigger. It's desirable that the models can be compared between groups, and also you can say, what would this model look like in a slightly different gravitational potential? That's an important thing you need to be able to do if you want to, as part of this mapping the dark matter distribution in the galaxy. These requirements are uniquely satisfied by torus-based models. They're models where you're founded upon the actions, and the key thing is the uniqueness and the adiabatic invariance of action enables you to achieve these goals. If you use other sorts of integrals of motion, you don't succeed. Torus modeling should be thought of, I think, as a variant on Schwarzschild modeling, but I'm arguing that it is advantageous not to assign the weights to orbits individually, but to assign distribution functions, analytic distribution functions to notional populations, and to adjust the parameters in those analytic distribution functions. It's important to take into account the visibility of tori, that's to say the selection function in the optimization process. Early models already revealed this. I mean, one thing I'm pleased about this is that this modeling procedure revealed this subtle error in the origin of the standard solar motion, but we do have a very long way to go before we're prepared to model the Gaia catalogue, but in Oxford we are at least working on the problem. Thank you.
Okay, any questions?
I actually have two questions. One is more computational one, and another one is more observational. I'll start from the computational one. Normally, the big simulations and big computations of galaxies or cosmological simulations, they take an enormous amount of computer time and things. Does the torus approach reduce the computational time and makes it this way easier to get torus models from different groups and then the comparison?
I think the answer there has to be no, and the reason is that the number of orbits you include, or the number you include in one of these models, or the number of particles you include in an n-body model always rises, so that your computational resources are comfortably stretched. I think that's the correct expression, right? So a crude answer I can give is I can compare the cost of finding a torus to the cost of integrating with a Runge cutter, and I would say that with the code we have at the moment, it's probably a factor of a few less efficient. So on your laptop you can calculate a torus, boom boom. It takes a second, or it's that kind of time. It's not a nanosecond. It's not a microsecond. It's on the order of a second. So it's not a costly business. And so, but I anticipate that by the time we go to production models, we will, have farms of, we will have clusters of processors grinding away, because we will want a large number of tori. And we will be spending more time, I think, on this fitting process. This sampling business is very expensive, as you can imagine, because you have to do integrals in high-dimensional spaces of the data. But I mean, everybody's going to have to do that. That's a universe.
My observational question is, as you mentioned at the beginning, there's large amount of surveys which have already been done, a few which have been carried on, but somehow I feel, or I fear, if you prefer, that there is some sort of fear around of people saying, all right, we just stop doing big surveys because we're just waiting for Gaia.
Oh, yeah. No.
And Gaia's going to, anyway, just going to destroy everything. So if you'd have a telescope for yourself,
yes,
and say, all right, now I want to do something now without waiting for Gaia, what would you do?
Work in the infrared. Gaia's big problem is a visible instrument, right? And it's not going to see the most interesting part of the galaxy. I mean, two interesting parts of the galaxy, right? The disk, the thin disk, and the bulge. So that's what I would do. And you can do anything, right? But proper motions, radial velocities, chemical abundances, these things could all be discussed. They're all interesting because you're probing terra incognita. So Apogee and Hermes are, of course, planning to do that, and I would adjust my program to complement theirs, I think, is, yeah.
Yeah, I have a question a bit related with what you say now. Precisely the center of the galaxy and many other places there is a lot of dust, so there is quite a fraction of the galaxy and many stars that are not visible. So how this is affecting in your models, or how you take into account, or you consider that it's something you see a part of the galaxy and the other side of the galaxy that we don't see because of the dust, the center is symmetric, how this is taken into account?
Yeah, so I didn't make this point, but one important reason why I'm passionate about doing dynamical models that satisfy Jeans's theorem and stuff is that it enables me to predict on the basis of what I do see, what I don't see. If I see a star here moving at this speed, and I believe in dynamics, I know, and I believe the galaxy is roughly in a steady state, that over there, where I can't see, there must be a certain number of stars that I can calculate, right? Because they're these stars at different phases of their orbits. So dynamics enables you to predict the structure of the galaxy in obscured places. On the other hand, it doesn't enable you to predict how many stars there are on orbits that you simply cannot see. And obviously there, we have, so the problem, for example, of the inner disk, is being inadequate. Gaia will not be sampling it. It is, of course, sampled in various ways, and Hermes and Apogee will be doing more and so on. The VHS will be doing and so on. We will have limited information about the inner disk, and we're definitely going to have to use our imaginations, and we're going to have to use observations of external galaxies to complement. So we are going to be able to adjust the values taken by the distribution functions only in some ranges of actions, and in some other ranges of actions we're going to have to use arguments of continuity arguments of similarity to other galaxies. But we are going to be able to predict what is present in some parts of the galaxy, like the other side of the galaxy at positions similar to the Sun that we can't see. And this provides actually an exciting prospect for, I mean, there's another problem that I haven't discussed, but is very exciting and absolutely we have to get on with, which is using these surveys to improve our dust models, right? Because if you Gaia is going to be a spectacular resource in this respect, because you will see many stars along lines of sight at reasonably known distances. So you will know what the obscuration is to various distances. But better than that, these dynamical models will improve. You will be able to improve on the information that Gaia gives you by imposing the dynamics on the model. So one of the things we have to do with the Gaia data is simultaneously solve for the obscuration, because the obscuration model is going to be very important for Gaia.
I'd like to ask you, because I don't know about the torus method, how do you define a torus, and in particular, how do you define the boundaries of each torus? You talk about family of tori. How do you delimit and define each torus? Well,
a torus doesn't have a boundary. That's one of its nice properties, right? So a donut is a two-dimensional structure. We see it embedded in 3 dimensions, so it has a boundary. But in its own space of 2 dimensions, it is boundaryless. The way we operate, to tell you roughly how we do this, will answer the question better than embedded in 6-dimensional spaces, right? Which is what we do is we take the analytic torus. So if we consider certain model problems, a simple harmonic oscillator, a 3-dimensional harmonic oscillator is one, the isochrone potential is another, Steckel potentials are another. So there are a limited number of cases where we have actually analytic solutions, and we know analytically what these things are. We take this and then we numerically construct a canonical transformation that takes this object, which lives in a toy space of very little interest to us, into the phase space of the real galaxy, and we tell the computer to adjust the coefficients in this canonical transformation so that when it arrives, it's consistent. Actually, all you have to ensure, remarkably, is that on the surface of this torus, in 6-dimensional phase space, the energy is constant. It turns out you don't need to do anything else. And we all know what energy is, right? 1/2 mv squared plus phi. So that's what you operationally do. So we don't need to do any boundary defining or anything. We just have this analytical solution, which unfortunately is in terms of angle action coordinates, which are not sort of widely, it's not in every of galactic dynamics. And and then you have this numerically defined canonical transformation, which is what the computer does instead of solving the equations of motion.
So at the beginning you said something about the migration, to test the migration, if the sun was born much closer to the center or not, and if
all this stuff,
moving or not. So I was wondering whether, with the present data, is something that you can explore already with your model, and if this is the case, also how your models that look like are, as you say, for a steady state, can be used to explore this issue.
Yeah, this is something we're still trying to feel our way towards, but the point is that at each instant, a given population has a distribution function f of j, and this distribution function then evolves into another distribution function following an orbit average Fokker-Planck equation. So you have a diffusion occurring in only a 3-dimensional space. Lacey, in the 1980s, I explored this idea a bit, and I had a student, Adrian Jenkins, who worked on it a bit. So what Ralph Schoenrich and I want to do as our next step, roughly speaking, is to take the kind of models that he was constructing for his thesis work, in which stars moved around, sort of Monte Carlo style, and understand how the distribution functions are evolving in this kind of a picture. So then you find which diffusion coefficients are necessary in order to drive this evolution. I'm not sure I'm answering that very well, and that's because I don't yet know exactly how this should be done. It's work in progress. But the key idea is that the distribution functions of individual populations, like the stars of a given age, should evolve by a diffusion equation in time. The coefficients, the diffusion coefficients, just like the heat conductivity in this equation, because it is just the heat conductivity equation effectively, the heat conduction equation, are carrying information about the strength of the spiral structure and that kind of stuff that you need in order to produce, in order to drive the evolution, which you think, looking at the observations, is the right one, is the one that the observations require.
I was wondering how dark matter is treated in this. Dark matter, how is it treated in the...
Dark matter?
Yeah.
Yeah. Oh, yes, right. Well, it's not. That is to say, you treat the dark matter as a distribution, rho dark matter, which contributes a potential and otherwise is inert. So at some future stage, you would like to make the dark matter a proper dynamical thing, right? So that's, in principle, it's not a problem at all. You assign it a distribution function f, dark matter of j. Bingo, there you are. And that would then evolve, at least properly, when you evolve the gravitational potential, you know, when you added some stuff to the disk and the dark matter would be crunched. So it's very easy to include it. The problem is, the reason I don't rush to include it, is that how the hell am I supposed to constrain it? So until I think we've gone a long way further with fitting the models to the observable things, so that we can do it with sufficient precision that we can make intelligent remarks about what the dark matter density is as a result of working out what div of the gravitational field is, it would be premature to stuff the dark matter in, because unfortunately I don't have any observational constraints other than those I get from the baryons. And I'm honestly not sure quite at what date that will be achieved. You know, I think I will retire before that's been done. But, you know, what does one have students for?
I have a question too. How do you consider the interaction between the different kind of components of the galaxy? Meaning things like recent studies that hint that the encounter of the bar and the spiral arm is producing star formation. So,
yeah, well, so when we are somewhat down the track and we have when we have made we've made some progress with refining the galaxy's potential, I would then like to introduce spiral structure, first of all, by doing perturbation theory. Another thing I didn't tell you today, why I'm passionate about torus modeling, is because it enables you to do perturbation theory properly. And if you look at every other branch of physics, perturbation theory is the key, right? If you're doing condensed matter physics, you think about excitons, phonons or whatever. If you're thinking about particle physics, you talk about Feynman diagrams. If you're talking about celestial mechanics, you talk about disturbing functions. Physics always proceeds by perturbation theory. Perturbation theory isn't merely a computational tool. It provides the language with which we understand things. It provides the means, the words we use to get a hold on physical phenomena. And we don't use it in galactic dynamics significantly. It's a problem. And the reason I think we don't is that its natural framework is angle action variables, right? And we traditionally haven't had good representation of angle. So I want to introduce spiral structure by perturbation theory so I can understand what's going on. Then, of course, I would like to do hydrodynamics, so numerical hydrodynamics in my perturbed gravitational potential, and thus incorporate find out about the shocks and this kind of stuff, which is the underlying physics, right? Which would be the source function. So I have a distribution function. Yeah, I get. So I at the moment, I'm treating stars as a conserved quantity, right? They're in this kind of model. They're just always there. At this later stage, stars would be created. There would be the distribution function. As you evolve the galaxy forward, new populations would come along to replace the old ones which are aging. But this again, it's a long way down the line. Not probably before I retire. There's plenty of work, I think, for people to do.
Thank you. So, any more questions?